So yesterday we discussed all these activation functions with its derivations and its range, domains, all those things. And we also seen this regression multilayer perceptron and what are the hyperparameters used here. So suppose if you want to build a deep network for regression purpose, you need to create this one based on this. What are the input neurons? How many input neurons you require? So these are the hyperparameters we use here. One is input neurons. Next is how many hidden layers and how many neurons used in hidden layer, output neurons and hidden activation functions and the output activation function and another is the last function. Last function you have to see. So here the number of neurons, input neurons in input layer depends on the number of attributes. Okay, generally, this is the features. And hidden layers based on your wish, based on the context of your problem. And then the neurons per hidden layer also depends on the context of the problem. But generally, we use 100 to or 10 to 100 number of neurons. But here for MLP, it is okay, 1 to 5 hidden layers. If more than these hidden layers use, that network generally called deep learning network. Okay. So here, the output neurons generally we use one for regression, and similarly for one for a binary class data. And what type of activation functions you can use in hidden layers, hidden neurons? So you can use either ReLU or CeLU and its a series as a activation function in neurons in hidden layers. And the output activation function is must. It depends on the problem. If it is a regression problem, you can use none or directly whatever the weighted sum comes into the output neuron, that will be the output. Or you can use the ReLU function and a softless function or logistic function. Generally, the logistic and this gives you values between the probability values. So that's why generally we don't use it for regression. And to make it, you require one loss function also. What is the loss function here? We will explain it based on the gradient descent. That loss function is MSE or MAE or RMSE. These are all the loss functions we use for regression. For this classification, we use the different loss functions. Those functions we will see here. This is the structure already we have seen. Suppose if you want to build a classification deep learning or MLP architecture, you should use these are the hyperparameters. One is this input and hidden layers, how many and output neurons, output layer activation function, and the last function. So the last function we use RMSE, MSE, and these for regression network. But for classification network, we use cross entropy loss function, RMS prop. These type of loss functions generally we use for classification problem because this cross entropy depends on the this function, this table, that is confusion matrix. So anyhow, how many inputs and hidden layers you have to use? It is similar like the regression. It is the number of units neurons required in input layer depends on the number of features used in your data set. And similarly, the output is also same thing. If use one or a binary class, then use one output layer, output neuron, and the if more than this, that is, you can use the more number of neurons in output layer and use the softmax function. So for a single layer, single label or a multi-label, use logistic function as an activation function in output layer. Okay, and softmax for multi-layer. So it's multi-class classification use the softmax as the activation function in your network. Suppose the network is like this. So this is the input layer. I am taking only one hidden layer. It is a input layer and it is a output layer. In output, if the data is a binary class data, only use one neuron at output layer and use either logistic function. Okay, and if the labels are more, labels means suppose it is a data set. In this data set, suppose assume that it is a output layer, output column here. Suppose it's yes, no, like this. Only two values repeated in the output. Use only one neuron, like the regression. If more than two labels used in this output layer, okay, then I use more number of neurons in the output layer, but use here softmax. Already we discussed them in yesterday. So here, these are all the neurons in the hidden layer. You can use either ReLU functions as an activation function in each neuron, and or the SELU function or a ReLU series in this. And what is the input layer? Input layer takes the values from, suppose this is one feature, second feature. This first record value, this value goes to this one, and this value goes to second neuron. This third value goes to third neuron, and this weighted sum suppose it is W1, W2, W3. So we check this as X1, X2, X3. So here W1, X1 plus W2, X2 plus W3. X3 is a weighted sum. We call it as capital I or capital II or IJ, whatever it means. So this is the weighted sum I will be fed to this neuron, and from this it connected to again to the next layer neuron. So this is only one calculation for one neuron. Similarly, you have to calculate this one. So like same weighted sum. It goes to ReLU function. That ReLU function gives you output. That output will be fed to all the neurons in the next layer. Similarly, here. Okay. So
Sir,
whatever.
for second hidden layer, we will get a different weights, sir.
Here, yeah, these are also weights. These are also weights.
Uh,
So everywhere, wherever you have the connection, okay, that connection has a weight. Remember that.
Same weights will be having or different will be having, sir?
Different. All are different. All are different. So those weights generally, the weights from all these connections. Okay. Suppose how many connections are there here? 3 into 3. That means 9 here. Okay. This is between first layer to hidden layer. And again 3 to 3. Again another 9. Suppose here only one neuron. If you use the output layer, you will use only 3 weights. Total 12 weights. All of you got it? All of you.
Sir.
Right. So here, this is one set of weights. These are all different. These are all different. Again, these are all different. Okay. So how you generate these weights? These weights are generated with random function. Random function. It generates the values between -1 to 1. Okay. You can generate any value, but generally the values we check between -1 to 1. But there are some theories how to generate these values. Suppose I have to generate the 12 values. If you use only one neuron in the output layer, hidden layer 3, and the input layer is 3. Actually, in real life, these are all in hundreds. These are also in hundreds. And again, so many hidden layers, and again, so many hidden layers. So finally, you may get one output layer. So based on the number of neurons increased, you will have the number of weights. Actually, in deep learning, in DL, in DL, there are millions, millions of weights you have to initiate first, and iteration by iteration. Okay, iteration by in training phase, iteration by iteration, all these millions of weights you have to update. You have to update iteration by iteration. So while updating all these millions of weights in this neural network, all those weights will be lens from your data set. What is the relationship among all these features will be fed to these weights via this training phase by updating the weights. What is the updating process here? So updating the weight already I'll show you this in MLP. WI is updated with the old WI plus eta into error of that into error of that into xi something. That formula we have seen and we have calculated. So for one weight, you require the error from the next layer connected to this neuron, and that connection weight will be updated with this process. So this is a simple process. Okay, all optimizers use different types of weight updation process to update the weights. So when while updating these weights, you may get some converged weights. That means how many times you update it, that value will be the same. Okay, there will be no further updation. That means it has exhausted, and you can stabilize those weights, and still you continue for the remaining weights. So when these weights are stabilizing, you will get the error less. So I told you that this is a original output given in the data set. Okay. Now I have to calculate the outputs using the updated weights. Okay, iteration by iteration. Um, this is the word. This is a calculated output value for this each one. So how you calculate with this network? We feed this input here. So this is the record, okay, or the row. When you feed it, you will get some output.
Waiting soon.
Hmm. Okay. So when you feed this input, this record to your network creator, you will get some value here. If it is a numeric value, you will get. Or if it is a uh, class value, you will get a class, whatever it may be. If there is a difference here, this is the calculated value. Okay, this is a calculated value. Suppose assume that if it is 20 here, if it is suppose 22 here, there is a difference. Or otherwise, if it is yes, but if it is no. So I have to check the difference here. So these type of mismatchings will be considered in this cross entropy loss function. So what you call it is, this is the error. So based on these errors, you have to make a function based on those error differences. You have to make a function. That function is called cost function or loss function. Why we check this loss function here? This loss function is very useful in updation process because how these errors are going down. Suppose the error is initially 10. So in the next iteration it is 8. That means what is the error? What is the original value? What is the predicted value? The difference. Suppose so 6, 4, up to so on. So that means it is decreasing. The error is decreasing. While the error is decreasing, you will get good accuracy, right? So what we require? We require to require the decay of these errors iteration by iteration. But sometimes the mentality of this error updation may be sometimes suddenly increase. Instead of after 6, it may be 16. So that means in this 16 previous updation of the weights went wrong. Okay, went wrong. So how it went wrong? The process. So that's why here you have to calculate where this deviation is occurring. So for this purpose, You require what you require? You require the gradient. Gradient of these weights. That means how you are updating the weights and where this error become bigger than its originality of a decreasing iteration by iteration. So that's why that gradient you have to identify at that point whether it is increasing or decreasing suddenly. So that gradient is nothing but the derivative, okay, partial derivative, partial derivative of your weights. These weights generally depends on the error harmony. Okay. So the error function is very important. To get the error, what you require? You require a model or network. So when you feed the input here, input to the network, you will get one output value. That output value will be checked, and if it is not equal, you take the error. That error is required to update the weights. And again, how these weights deviated in its natural process of decaying the error, you require this loss function or cost function. Okay, that loss function you will create or define based on the values, error values, iteration by iteration. So this loss function gives you where this deviation occurred in decay. So to find that deviation, you require a loss function. That loss function is again derived on the errors. Have you got it? Any doubts till now? All of you.
No, sir.
Anyone? No. Good. So now tell me, what is the gradient? What is the gradient? Gradient is a derivation of the loss function. What is the derivation? Derivation means the change in its value from the previous step or iteration. Why we use this gradient or a derivation of this loss function? To know whether there is a steady decrement in error or not. If there is a steady decrement, you won't get the derivative is equal to 0. So that's why you require this derivation. Why we require this derivation? When you find somewhere this derivation is a 0, that means there is a sudden increment or decrement like this. Suppose if you make a function, loss function, so these are the error values. Okay, these are the time steps. Okay, or otherwise these are the time steps. These are the error value. Suppose these error values function is like this. Suppose here it is decreasing, but suddenly suppose it is increasing. What's meaning? While decreasing this error, suddenly at this point it taken the increment. That means here there is a deviation in updation of the weights. So to control those updation process in the weights, you require to identify at which step it has gone suddenly or shoots sudden up. That means here the error becoming big. So this is the error. Okay. So the error is getting down. This means what is the error? Error is almost 0. But suddenly it has increased this. Again, the error is this much. So that's why you should not get this increment in decay of the error iteration by iteration. So that's why for that purpose you require the gradient and you require the loss function. The loss function is derived based on what? Error values. Error values step by step. How do we get this error? This error is nothing but Oj minus Tj. Oj is a predicted value. Tj means a original value in your data set. How do you calculate this Oj? The Oj depends on the DL network or MLP. Okay, so how do you get this OJ value? When you feed this instant or the data point from your data set, iteration by iteration, you'll get a different output value. Okay, so you have to give input here. So that input for each input using this constructed neural network, you will get the own value, predicted value. We treat this one as OJ, and the corresponding TJ original value is there in your data set. The difference is generally called the error. Based on these errors, you have to derive a loss function. This loss function is used to know where this loss is increased or decreased. For that, this gradient is nothing but derivative of loss function. Derivative of loss function. So that loss function gives you where this error suddenly increase. So there you have to control this one. So this error, based on these errors, you will derive one loss function. Again, these errors are used to update the weights. So based on this updation of the weights, you may get a sudden decrement or increment of the error. So that's why where this error suddenly increases its error value. To know that one, you require the derivation of this loss function. So based on that, at that step, you have to update the weights with a particular optimizer. Okay. These optimizers generally used to update the weights. Still, while keep on increasing or updating the weights, okay, updating the weights, so these weights will be stabilized somewhere, okay, stabilized. When you have the stabilization of all these weights, there you will get a small error or the loss becomes a zero. Then you can fix this model along with your weight space for further prediction or deployment of all these weight space along with the model for further utilization. This is the process. Any doubt till now? Any doubts?
Sir, once it is stabilized, that's all.
Stabilization.
Yes, sir.
Yeah, stabilization means like this. If shall I clear all this?
Yes, sir.
Right. Now, stabilization means like this. Suppose I am taking only one weight and then you can apply for all. Suppose W1, weight 1, I am updating. For updating of this weight, what you require? The old weight in the previous iteration plus and what you got the output, okay, into learning rate into error, right? So this is assume that it is at iteration 2. Again, go to the iteration. Already my updation process completed. We treat this as W1 for the next iteration, right? And there is assume that there is a change. That change is delta W1. That delta W1 is nothing but this one. So this change depends on the error you got in this first iteration and this learning rate. What you get as a output, okay, and what is this target value? So whatever may be, that formula is there. Okay, I have updated. Assume that this is some 2.6. Okay, after updation, you got it as suppose 2.4. And see the similar process, okay, using this weight, again, I fed the second instant or second row to this model. So in between model will be there. That model gives you again some output. Based on that output and its error, again we are updating this way. So here, after third iteration, you got this. After fourth iteration, suppose you got 2.9. After fifth iteration, the weight updated as 2.92. Again, it is 2.91. Again, 2.9, 2.9, 2.9 up to so on 2.9. So that means this is called a stabilized. So how many iterations? This is the fourth, the fifth, sixth, seven, eight, nine, 10 up to so on 100. Even you iterate this training in the training process 100 times, this value is the same after suppose you take this fourth, fifth, sixth, seventh. After seventh iteration. That means this value has stabilized. You cannot change these weights after so many iterations also. Hello, you got it? Hello, you got
Yes,
it?
sir. Yes, sir.
Yeah. So what we use this weight? This weight is used to calculate the output. Yes or no? To calculate the this one output, what you require weights are required. Suppose if you take the previous network here, assume that this weight is updating. Okay, first time, second time, third time. After seventh time also, after seventh time or 200, this weight is same. Whatever it may be, this weight is used to calculate the output at this output layer. Yes or no? So when you have stabilized, when the weight is stabilized, the output at output layer will be the same. There will be no change. So still, if there is a output value after stabilized weight considered for your calculation of the outputs and with the original value in the data set, okay, for a corresponding instance or input. So still the error is the same without any changing, you cannot reduce this error after that iteration. So this error may be anything, not a small one. You can't treat that. Suppose the error is 50. So when these weights are stabilized, you cannot reduce this error to zero. Okay, all of you got it? All of you got it?
Yes, sir.
So that means you cannot accept that deep learning network at this stage because you are unable to reduce this error to a small value zero. That means you should not use this DLN. Suppose the other situation, the error is very small, 0.001 after 100th iteration. That means the error almost converged. Yes or no? Almost it is very small so that you can accept that model, okay, after some iterations. So here this convergence and the second one is stabilizing. So here converged to zero, here it is not converged to 2, that means stabilized only at 50. These values are stabilized. So that means in this situation you cannot use that deep learning network. But at this stage you can use that deep learning network for further prediction. All of you got it?
Yes, sir.
Yeah. So Manaki, if you have the lab section, that will be nice, but it is not possible. Okay. Anyhow, I'll show you how to try and how to get the errors, all those with one class. So that yesterday, I hope all of you got some good experience on this, how to check the hyperparameters and how to tune them to stabilize. But how to get that error only you can see in deep learning laboratory. That I'll show you tomorrow. Right. Now we go for further. What is the use of these optimizer? So the optimizer generally very important to update these weights because the optimizers are so many. In the previous one, only we considered the gradient, right? But in some cases, again, how this error is changing, and in the change, again, what is the change? Generally, we call it as a movement acceleration. So based on that acceleration, you can take the precautions in updation of the weights. So who takes that one? That is called a optimizer. There are varieties of optimizers we use, and there is another regularizer also we use. What type of features you have to consider for your training of your network, that is another important. Okay, so what are the features generally contribute in training process? We keep them and use this features will be de- deleted in our training process. So eliminating these useless features from our training part is take care by this regularizer. Optimizers take care about the updation of the weights. Okay, this depends on errors, and the regularizers also depends on the errors. By eliminating some of the features, you may reduce this error value iteration by iteration. So for both of them, what you require a function based on the errors, that is called the loss function or cost function. Okay, so the cost function, loss function is very important in weight updation process. That is useful for identifying where this error changed drastically with out of its nature, and that is useful, very useful for optimizer and regularizer also. Okay, so the loss function, what type of loss functions are there? We'll see that one. And what is our entire goal here? What is our entire goal? What is the goal of training process of any MLP or deep learning or any model? Anyone? What is our goal? Anyone? Any answer is okay, acceptable. That may be right, that may be wrong. What is our goal in this training process of any model, deep learning or MLP or any other models, machine learning models? Hmm? Our goal is our model should give you the exact value.
Accurate
As
values to get.
every value,
Accurate values we can predict or we will get the values.
you have to predict the accurate value exactly as it is, like the value exists in your data set for any corresponding row. Yes, that is our aim. That means what? The error must be 0. How do you get that error will be 0? By adjusting the weights. How do you adjust the weights? These weights adjusted based on the error values and using the optimizers. So that the tuning of your weights depends on hyperparameters. Hyperparameter tuning. Why we tune these weights? We tune these weights to get the error small or 0. So for that purpose, this loss function is required. So that loss function contributes its contribution to both optimizer and regularizer. What is the work of regularizer? The regularizer reduces the number of features used in your training process by estimating the error or loss value. The same error function or loss function is used for optimizers in updation of the weights. How it contributes to this optimizer? The loss function gives you the loss variation. Okay, that's when you take the derivation is equal to 0. At that point, how this loss is changing at which step? So at that step, the optimizer takes extra care in updating the weights. Okay, so always you require in training process, you require the decay of the error iteration by iteration. That is our goal. Okay, like I hope I discussed about this one. Suppose you are the new for preparing some of the items, okay, food items. You will try with some combination of the spices or some combination of items to prepare. Suppose you take a chicken biryani. So preparing this chicken biryani, what you require, what type of items you require, how much quantity you require, and what is the process? The process is nothing but a model, and the quantity is nothing but the weights. Okay, so you have to add. Suppose after first attempt, you may get a bad dish as an output. It is not tasty. That means you will find where the wrong occurred. Suppose the salt is too high. In the next iteration, you will reduce it. While reducing it, if you reduce too much, again your dish will be the wrong dish. So that's why again in the third attempt you will take it moderate. Similarly for spice, okay, for chili powder, for some other ingredients, so after adjusting all those things in iteration by iteration, attempt by attempt, you may get a good dish. So that is nothing but weights stabilization. When the weights are stabilized, you will get a good dish. Weights are nothing but quantities. So for each ingredient, you will have a quantity. Quantity tuning is very important. So to tune these all, what you require the error, how bad it is. Based on that, you have to tune your weights. So there are different optimizers to help you in updation process. Okay, so those are called optimizers. There are different varieties of optimizers we use in deep learning. That is HGD. So this is the base optimizer after gradient, and then Adam, and then RMS prop, Adam Max, Nardam. Okay, ADA Delta, ADA W. These are all different varieties of. So many are there. There are different varieties of optimizers for updating the weights. You can check any one in training process. And the role of the regularizer is to ensure that the trained model generalizes to new data, okay, to stop this overfitting. So this regularizer generally, yesterday we used it 30%, 5%. Okay, you stop it, drop from the training process. Suppose there are 100 records, you can delete some of them. Anyhow, I told you there are a lot of loss functions, object functions, or cost function, all are same. These are all different varieties of functions we use for loss functions, and by using these, you may get some of the feedback from it, and that feedback is used to optimizer in updation of the weights, updating process of the weights. Okay, so binary cross entropy. These are all the classification related loss functions or object or cost functions. Binary focal cross entropy, categorical category. These are all related to classification related functions, right? Again, Poisson distribution, these hum or loss cost, these are all also very important. These are okay. Mean square, mean absolute. This is MAE. This is MAPE, and this is MSE. These are all the loss functions. Okay, MSLE. These are all the loss functions used for regression problems. So these are all used for this classification. Similarly, these are all some of the classifications, hinge functions. These are all for classification. We use these last. And there are some optimizers already we discussed. ADA factor, okay, Adam, W optimizers. Okay, deserialize. This is the process. This is also process, and these are the L1, L2 regulars. Yesterday, I have seen in this visualization of networks, right? And activation functions are these LU, RELU, okay, and those are series is linear function. Okay, these are all we have discussed. Okay, sigmoid function, softmax function, soft class, soft organ. So not only these, so many are there activation functions, but the latest good functions are Adam series. Those you can use for your hidden layers. But there is a fixed activation function you have to use at output layer. Sigmoid function when you have only the numeric values at output column in your data set. Another is if it is a binary class data. This is a regression. This is a classification. When you have more number of labels, okay, in classification, you have to use softmax function, soft plus also. Okay, okay, these are all different varieties of all these regularizers. All this. So now you have to tune how to tune your neural network for the deep learning using these hyperparameters. So fine tuning your network is very important. Okay, you can fine tune this network using these hyperparameters. What are the hyperparameters here? Already we discussed some of them. So the number of layers, number of neurons, okay, activation functions, optimizers, regularizers, okay, normalizations, batch sizes. These are all different varieties of hyperparameters. So you can tune all of them, all your models using one service is there. That service is AutoML Suite is available in cloud services. Mostly in AWS, you can get it. So here there is no need of experimenting. So this AutoML should, if you use it, you have to pay some money. That AutoML should tunes these models using the hyperparameter combination. So in preparing the dish, okay, chicken biryani, I told you that first time salt is increasing, second decrease it, third time moderate it. For similarly for other gradients, so you require so many combinations. At which combination you get a good dish, you don't know. So you need experimenting so many times. So all these times are experimented by this AutoML with the different combinations of all these weights, hyperparameters, you'll get a good weight space. So for that purpose, there is one software available. The suite is available in cloud services. Okay, you can use it, but you won't get any knowledge by using this AutoML. You should know how to tune your network using the hyperparameters. So now the first hyperparameter is the number of hidden layers. What are those number of hidden layers? So, except this input layer is fixed based on the number of features available in your data set. Output layer is fixed based on the number of labels available in your data set. In between this input and output layer, you can use any number of hidden layers as you wish. But there is a theory how to use these hidden layers, how many numbers generally suitable for this. For complex problems, generally you have to take more number of hidden layers. Okay, have much higher parameter efficiency than the shallow ones. That's why you take more number of hidden layers. If it is moderate, you take the moderate number of this. If it is a low hidden layer model, so these are generally very useful for small type of the data, very uh, less complexity data set. So you take almost based on the complexity of the data set, you have to use your mind in selection of a number of hidden layers. Okay. Nana Eleva, sorry, sir. Now, how to improve your random dropout is another hyperparameter. How much dropout you have to take? Suppose there is a network here, so many hidden layers. So this is the output layer, and there are so many connections. This again, this. So many connections from layer to layer. Okay, like this. So in these connections, sometimes if the model overfits, what you need to drop some of the weights here. Okay, so that means if you drop some of the neurons, if you take 20 neurons in this layer, if you drop 10% means two neurons, if you drop, all these connections will be nullified. That means the weight space will be reduced. When you take unnecessary weights, more number of weights, this model also becomes complex and that becomes overfit. That's why you have to reduce some of the neurons here. Okay, that means you nullify some of the neurons. Automatically, its connections also will be nullified to the next layer. So that sometimes you may get a good accuracy. So that is called a dropout. That percentage must not more than 40% in the entire training. Okay, you should not nullify more than 40% of the neurons. Okay, that should be less than 40 only. So when you test the accuracy is more than the training error. Suppose the testing accuracy is more than training accuracy, increasing number of epochs. That means that becomes a overfitting. So the test accuracy must not be more than the training accuracy. That means if the test accuracy is more than the training accuracy, that is a overfitting. That means what? Already in training phase, that model seen more number of times of the records used in the training data set. For that purpose, okay, already on seen data, you got something, suppose it is 90% of the accuracy. But on unseen data, suppose you are getting suppose 95, that means something went wrong. So that's why the test accuracy always must be less than the training accuracy. So the dropout generally we don't apply on this testing. Only in training phase we use this dropping after testing. Again, you have to retrain that model. If still the error is same, we might be not training for long enough. You just drop that model. You check the new model. Okay, and then or otherwise you increase the number of epochs. That's it. And testing the different optimizers. So these optimizers generally used to update the weights. So already we discussed SGD, Adam, RMS. SGD used only gradient descent, and Adam used a gradient along with some other factors that is based on the momentum and acceleration. So what is the difference between gradient, momentum, acceleration? So the gradient is nothing but the derivative of any function, first derivative. When there is a second derivative, that is called acceleration. Why we use this? Suppose there is a last function here. So how do you know where this error is bigger or smaller or turns the next level? So what is the meaning of this? It is decaying here, but here the derivative of the function is always equal to 0. So at this point, again the error is increasing. So you have to identify these type of points. Okay, and so to get this one derivative, this the derivative at this, at this, at this, at this, all are equal to 0. We know that. But whether at this point either increase starts increasing or not, to get it you require second derivative. So see the second derivative, if it is the positive, what it means? It starts loss increasing. If the second derivative is the negative, it start decreasing. Okay, that type of concepts are used in both AGD and RDM. RMS prop also depends on this acceleration and gradient. All the latest optimizers use the base derivation and its second derivatives also. Okay, so now some of the objective function we will see tomorrow. Already time. Okay, in the next class, so I'll finish this one. Okay, this unit. So here, how many prejudices are there? 13. Number 1. Number 1. 1 is absent. 2.
Present, sir.
3, 4, 5, 4.
4 present, sir.
5, 6,
6 present, sir.
7, 8, 9, 10, 11, 12,
Present, sir.
12. Where is
12
12?
present, sir.
ఎక్కడుందమ్మా నేను ఎవరు
11
కనబడలే?
present, sir.
Who is 12?
Sir, 12 present, sir. Pratyusha.
Number, okay, right. 12 is okay. 13?
Sir, 11 present, sir.
11 present, okay. 13? 14, 15, 15. Pujita. 16,
Present, sir.
17,
Present, sir.
18,
Present, sir.
19.
Present, sir.
Okay, right. You can leave.
Sir, 19 also present, sir.
Okay. 19%.